Is that okay? Okay.
I think we can start. So I'd like to welcome everybody for the last day of last session of our little conference. And it's a pleasure to have Jean Dussault on the, well, now it's the Institute, it's video tech, who's going to talk about the dualities between genus zero, Y, and the Hodge.
Okay. Thanks a lot for the introduction. Yeah, first, thanks a lot to the organizers who put together this very nice conference. I enjoyed this week a lot, and thanks for the invitation. So yeah, today, I want to explain some kind of dualities between different genus zero wild non-abelian Hodge spaces. And so what is the general context? So the main objects that I will be interested in these talks and that I'm interested in my research are wild character varieties, and they are moduli spaces of generalized monodromy data or Stokes data of meromorphic connections with irregular singularity. And the thing is that to get such a wild character variety, you have to fix some initial data, something that you can call a wild Riemann surface. That's you fix the base surface on which you have your connections, and you have to fix some singularity data characterizing the shape of the singularities. And then there is a quite striking fact, a quite intriguing fact, is that it turns out that several wild character varieties coming from different wild Riemann surfaces can be isomorphic. So for example, they can correspond to connections with different ranks, different numbers of poles, different pole orders. And so in some sense, you can say that you have several representations of the same abstract moduli space coming from those different wild Riemann surfaces. And a related thing is that if you look at isomonodromic deformations of connections, you have kind of the same phenomenon which manifests itself in the existence of several lax pairs for Painlevé-type equations. And we saw some examples of that yesterday in Martin Stokes in his degeneration scheme of Painlevé equations. There were several different lax pairs sometimes appearing for the same Painlevé equation. And so, this motivates some kind of big question is, could we classify those wild character varieties? Can we understand systematically isomorphisms between them? And today, I want to tell something which goes a little bit in this direction. I want to describe a combinatorial way in genus zero to obtain several wild Riemann surfaces which are conjecturally, which are expected to be representations of the same moduli space. And this generalizes some cases that were already known to the case of arbitrary irregular types of genus zero. And I also have to say that it is based on some work that I just put on the archive. So that's for the general idea. And now what's the outline of the talk? First, I will spend some time explaining what Stokes data are and wild character varieties. We already met them several times this week, but maybe, I think it's still good to spend some time explaining the context. And then, I will go to my main point, explain how I can get in this combinatorial way some expected dualities between wild character varieties. Okay, so just to fix ideas. So we consider a fixed smooth complex algebraic curve, sigma, and here today we will only work in genus zero and fix once and for all sigma equal to pi1. And the objects that we consider on them are like vector bundles equipped with an algebraic connection on pi1 minus a finite number of singularities. And a bit more explicitly, if you choose a trivialization locally of your bundle, such a connection is just an operator like this, nabla equal d minus az dz, where A, it's a rank n by n square matrix, which may have poles at the singular points. And so this is just a slightly more geometric viewpoint on those very classical objects that are systems of linear differential equations, because the horizontal section of this connection is just a vector y, which is solution of this system of complex linear ODEs. So if you have such a connection, it defines a monodromy representation if you analytically continue its solutions along paths on sigma minus the singular points. And so you get, the monodromy representation of pi1 of, it should be sigma minus the singular points into GLNC. And more explicitly, you can choose a basis of the fundamental group of sigma without the punctures, like this, and this defines some monodromy matrices, the monodromy of the connection around those singularities. And so with that, you see that you can write down explicitly what is the moduli space of those monodromy data. It's just a tuple of matrices M1 to MM. And since there are no other singularities, you have the condition that the product of the monodromies has to be equal to 1, and you then quotient by GLN because you forget the framing, the choice of basis at your base point B. And it turns out that this space, it's called the character variety, and it's a very interesting space. It has a rich structure. For notably, it is a Poisson manifold, and there are several viewpoints of these structures due, for example, to Attila-Bott or Goldman. And if you fix that, the monodromy matrices have to live inside some conjugacy classes in GLN, you get symplectic manifolds. Okay. And the thing is that when you have regular singularities, so which more or less means simple poles, then it turns out that this monodromy representation entirely characterizes the connection you start with up to isomorphism. So in terms of moduli space, you can define a moduli space of connection. So connections with regular singularities at the singular point up to gauge equivalence, which in terms of the bundle, it means a change of trivialization. And in terms of the linear system, it just means meromorphic change of variable z equal g y. And so you have this moduli space of connections. And in the case where you have regular singularities, there is an isomorphism between the moduli space of connections and the character variety, the moduli space of monodromy data. But we run into trouble if we consider now irregular singularity. That is a connection with basically higher order poles. So you have your matrix A, which has, if Z is a local coordinate at one of the singularity, you have a Laurent expansion with a polar part like this, and with a pole order higher than 1. And in this case, it turns out that the monodromy representation of the connection is still defined as before, but it is not enough to reconstruct the connection to keep all the information about the connection. And an example that I can show to convey this idea is the following. So if you consider this regular singularity of rank 1 with one regular singularity at 0, its monodromy is exponential of 2i pi times this coefficient lambda. But I can also consider a near-regular connection of a similar form. I add this factor dq, where q is a polynomial in z minus 1, and it has the same monodromy. I can choose any term q, and it has the same monodromy, but they are not gauge equivalent. So you see, if I want to get all the information about the connection, I will need some extra data. And that's where those generalized monodromy data or Stokes data come into play. But they will allow me to have, as in the regular case, a topological description of irregular connections. And so, the thing is that the shape that those Stokes data will have depends on the connection, and more specifically, it depends on the formal normal form of the connection. This formal normal form is provided by the classical Turretin-Levelt theorem, which was already mentioned several times this week. And yeah, here I'm stating it in this maybe slightly imprecise way, but maybe more explicit like this. So it's always possible if you to apply some formal gauge transformation, so some formal series gauge transformation to reduce your connection in the vicinity of a singular point given by the local coordinate z equals 0 to a formal normal form of the form like this, d minus dq minus lambda over z dz, where you have this q, it's a diagonal matrices, and its entries are polynomials in z minus 1 with possibly a ramification. Possibly you have to take a root of your complex variable. And so these QIs, yeah, they are called the exponential factors of the connection, and the collection Q is called the irregular type. This integer R is the ramification order, and I will say that the connection or that the irregular type is untwisted if it's just one, so there is no need to consider ramification. And the case of regular singularities corresponds exactly to this case where this irregular type vanishes. And then we have this matrix here. It's a constant matrix called the exponent of formal monodromy. And yeah, basically it's a block diagonal matrices. And the blocks, they correspond to the distinct QIs, essentially. If I have several exponential factors are the same, I will have a square block in this formal monodromy corresponding to to this exponential factor. And so, yeah, and I can encode this formal decomposition in a slightly different way. I will, say that like formal data, local formal data of connection are a pair consisting of an irregular class, where it's just the collection of the exponential factors, but I forget the order compared to the irregular type. And here it's the multiplicity. If Q1 appears like twice here, it has multiplicity twice, etc., etc. And yeah, up to isomorphism, what is important is not basically lambda, but the conjugacy classes of the different blocks of lambda. And so this data of theta and c, what I call local formal data, it is exactly the isomorphism class of such a formal normal form. So that's what the data I use to characterize the formal data of my connection at my singular point. Okay, and now, yeah, the fact that we will need Stokes data and that they depend on this formal data, yeah, that's what is referred to as the Stokes phenomenon. And yeah, I can try to give some intuition for this. And the idea is basically the following. So if you look at this formal normal form, a solution of it is exponential of Q, this irregular type, times Z to the power lambda. And so you see in particular, like components of this will be linear combination of exponential of the small QIs. And the thing is that, yeah, the asymptotics of this exponential term, exponential of QI, they will change depending on from which direction I approach the singularity. And the consequence of that is that I will only be able to find true solutions asymptotic to my formal solutions if I restrict to some sectors around the singularity. And I can visualize those growth rates when I approach the singularity nicely by drawing what I call what we can call a Stokes diagram. So yeah, namely, you will draw exponential of the real part of Q depending on the angle, because the growth rate is controlled by the real part of the exponential factor. And so, for example, in this example, I draw it for a cubic exponential factor like this, and you see it does something like that. And here, like the dotted circle delimitates the zones. Here it's growing, here Q is decreasing when I approach the singularity, etc. So I can visualize those growth rates on the Stokes diagram. And the way those like generalized monodromy data appear is that I have to kind of compare those growth rates for pairs of distinct exponential factors. And Andreas kind of explained this in more detail in his talk. But I will still say a few words here. So here it's an example of Stokes diagram with two exponential factors of degree 2 with different coefficients. And we will single out some particular directions around the singularity. The singular directions or also called the anti-Stokes directions. And there are directions where the difference between the growth rates of some pair of exponential factor is maximal. So here I've just drawn one pair of exponential factors, and to this pair are attached, here you see, 4 singular directions. It's like, yeah, when the distance between the two circles is maximal. And yeah, as Andreas explained, I mean, there is this construction you can do with adding some punctures defining this extra surface, and you will add exactly one puncture for each singular direction. But like the upshot of all that is that you will be able to define a Stokes matrix associated to every arrow between Qi and Qj associated to such a Stokes direction. So for each pair ij and each direction, which is a singular direction for the pair ij, you will have a non-trivial entry. We'll have a Stokes matrix in the singular direction D, and you will have a non-trivial entry in the Stokes matrix corresponding to the pair ij. And besides that, like you have diagonal coefficients equal to 1 and all other coefficients equal to 0. So I get Stokes matrices like that. And so it turns out that, yeah, every connection can define in a more or less canonical way such Stokes matrices. And the upshot of this is that you can get a similar construction of wild character variety, an analog of the usual character variety. So it will depend on the global version of the formal data, that is the collection of the shape of the Stokes matrices will depend on like the collection of the formal data at every singularity. And yeah, you can get an explicit presentation of the wild character variety compared to the usual character variety. You just have to replace this topological monodromy mi around the singularity by a more detailed product. So you will have connection matrices, a product of Stokes matrices whose shapes I just explained, and hi, which yeah, basically corresponds to the formal monodromies. And you have an explicit description like that of a wild character variety. And same as the usual character variety, it has interesting geometric structures. Yeah, you can endow it with a quasi-Hamiltonian structure that was done by Boalch. And yeah, same as the usual character variety, you can fix the formal monodromies to lie into some prescribed conjugacy classes and do a Hamiltonian reduction. And you get a symplectic variety if you do this. And yeah, the nice thing is that, as in the regular case, if you do that, you have a one-to-one correspondence between irregular connections and their Stokes data. And so, yeah, you get an isomorphism between a moduli space of irregular connections with prescribed with prescribed irregular class theta, and the wild character variety of the Stokes data whose shape is determined by theta. Yeah, sure. Yeah. So the hi, yeah, there are some subgroups of, yeah, I didn't, yeah, there are some subgroups of GLN, and the shape of the subgroups, it's basically like this, it's this lambda that I showed, like, it corresponds to like the blocks, those blocks of lambda. So basically, yeah, the shape of H, it's like some block diagonal matrices, and the size of the blocks depends on like those multiplicities, essentially. Yeah. Yeah. Uh-huh. Yeah. Yeah, it's possibly a block because, and the size of the blocks, yeah, it depends on the multiplicity of Ni and Nj. In many common cases, it's just one, but yeah. So in some sense, you can view it as a matrix with like non-commutative entries. Okay. So yeah, okay. So all this was, yeah, maybe I was going a bit fast, but like to make this more explicit, let me show you a simple example, which, yeah, is the same case that like Andreas showed us. So the pure Gaussian case, I have 2 exponential factors, all of degree 2. And so you see I have this Stokes diagram, and so I have 4 singular directions. And so yeah, I get that like the wild character variety is like this. A product of Stokes matrices equal to 1. And the formal monodromy here, the connections matrices, they vanish because there's just one singularity. So yeah, by change of framing at the base point, I mean they disappear. And so yeah, I have 4 Stokes matrices, one for each Stokes arrow like this, and they are alternatingly upper triangular and lower triangular with ones of the diagonal. And here, yeah, so H is like just diagonal because the multiplicity of Q1 and Q2 is 1. So this is my my wild character variety in this quite simple case. No, capital H is yeah, it would be just the diagonal matrices with non-zero coefficients, like invertible diagonal matrices. Okay, and so yeah, I'm not going really to I'm not really interested that much in isomonodromic deformations today, but still, I will need some ideas that come from that, like to characterize like in what comes later. So yeah, I will just say a few things. So the idea of isomonodromic deformation, it appears when you ask the following question, you want to move the position of the singularities and you want to deform your irregular class. What we will call isomonodromic times. And you ask how the connection should change for the Stokes data to remain constant. And schematically, it's kind of nice to view it geometrically in this way. You will have a base space B of deformation parameters of your isomonodromic times. And over this base space, you have a fibration, a family of wild character varieties. For each point in the base, you have a corresponding like globally irregular class and positions of the singularity, and you have the corresponding wild character variety. And asking for isomonodromic deformations, you want the Stokes data to be locally constant, which I can represent like this with those horizontal lines. And the RAM side isomonodromy, where you have like equations, differential equations satisfied by your connection, basically you can view it as like if you transport this Betti picture of isomonodromy via the Riemann-Hilbert-Birkhoff correspondence, you will get such a fibration on the RAM side. But then the horizontal foliation is complicated, and it's given by those complicated nonlinear PDEs, the isomonodromic deformations. But here, I'm more interested in like, what is kind of the universal, the largest possible space of times? And just, let me mention that like, if you do that, depending on the choice of wild Riemann surface, you can get all Painlevé equations. For each Painlevé equations, there is a choice of wild Riemann surface such that, this story basically corresponds to the Painlevé equation. So, let me, focus on like the space of times. In the regular case, it's very natural. The only deformation parameters that you have are the positions of the singularities. And the only constraint when you move them is that like distinct singularities have to remain fixed. Here I'm really not looking into coalescence, because otherwise it's not like completely clear like what it would mean to have the same monodromy if you change the number of monodromy matrices. So the space of times in the regular case is just the configuration of n distinct points in pi1 here, if I'm on pi1. And in this case, if you take the case with like 4 simple poles on connections of rank 2, SL2, and then you can parameterize things in such a way that like the isomonodromic deformations lead to Painlevé-6. But now, what happens about the space of time in the irregular case? Now I want to move not only the position of the singularities, but also the coefficients of my irregular type. And so here I'm just focusing of, let's say we fix the positions of the singularity and we just consider moving the QIs, the coefficients of my irregular type. So concretely, here I'm just looking at the untwisted case for now, but you can also set up things in a twisted case where you have ramification. So I can write my irregular type like this, and I can give a name Aij to the coefficients. And what I want to deform are those coefficients. And so, but I cannot deform, there is still some constraint on my deformation. which is the analog of the fact that the singularities are not allowed to merge. And what is this constraint? The constraint is that the degree of the difference qi minus qj has to be constant. Why? It is because the number of Stokes arrows or like of non-trivial entries in a Stokes matrix which are associated to any pair ij is given by this degree. So if I change this degree, the shape of my Stokes matrices will change. So same, it's unclear what it would mean in that case to say that I have the same monodromy if I don't have the same shape of the Stokes matrices. So yeah, I say that we have this admissibility constraint. We have admissible deformations when we could have deformations of these coefficients such that the degree is constant. And so, now that you have this definition of admissible deformation, you can wonder what are like equivalence classes of irregular type. This defines an equivalence class on irregular types. And so, the very simple case is like if your leading term has n distinct eigenvalues, so that those degrees are n for all pairs ij. And then the only constraint is that like the coefficient of highest order have to remain distinct. I move them, but they can remain distinct. And the other coefficients, they can do really whatever. It doesn't contribute to the shape of the Stokes matrices. So in this case, the space of times is homotopy equivalent to the configuration of n points where n is the rank, because the other coefficients, they don't count. But like if you have non-generic irregular types, so if you allow for having several identical coefficients in the leading term matrix, then it's a bit more complicated. But at least in the untwisted case, it's quite easy to figure out how to characterize equivalence classes of admissible deformations. And we can do that with introducing what one can call a fission tree. And I will just like illustrate the construction on an example. You will see easily what's going on. So let's consider this example with rank 3. And like I have this leading term coefficient, and you see it has two identical coefficients here. And like this one is not identical. So you see here, the degree of the difference will not be 2, but it will be 1, while the other differences will have degree 2. And so, I will represent it like this. First, like, I have two distinct coefficients at my height 2. But then you see those two, if I go to the next subleading term, they split into -1 and 1. So I represent it like this. The two coefficients split, and this one, it remains like this. And so, I characterize kind of like the equalities these splittings, if I start from highest degree to lowest degree, by the data of such a tree. And it turns out that in the twisted case, so where you allow for ramification, it's quite more subtle because your exponential factors, because of the presence of the root, are kind of multi-valued, and you have to take into account the difference qi minus qj's between the different determinations of the root. But you can still define some kind of fission tree in that case. And we showed in some work with Boalch, Gabriele Rembado, and Matteo Tamiozzo that even in the twisted case, and in some cases with like G bundles, here I'm only focusing on GLN, but also in some cases with like G bundles, you have an equivalence between equivalence classes of admissible deformations of local irregular classes and fission tree. So you have this combinatorial object which characterizes the irregular classes up to those admissible deformations. And the space of time, so your space of universal deformations, local, can be explicitly determined starting from the tree. And so this is the local case where just to have one singularity and I move the irregular type, but you can do that if you have several singularities, and you can define the fission forest, which is the collection of the fission trees at each singularity. And so, such a fission forest corresponds to a class of admissible deformation of a global irregular class, so a collection of local irregular classes at each singularities. And so if you have that, you see that up to isomorphism, actually your wild character variety, it depends not really on the irregular class theta, but just on this kind of like topological skeleton, just on this fission forest. And so the question of like classifying wild character varieties kind of boils down to, yeah, given like such a pair with a fission forest and like conjugacy classes for each, and a conjugacy class for each leaf of each tree of the fission forest. This gives me a well-defined up to isomorphism non-abelian Hodge space. And so, yeah, can I understand which such pairs give rise to isomorphic wild character varieties? That's kind of a way to, yeah, reformulate the question. Here, yeah, I would say, yeah, as an algebraic variety and like possibly also like the symplectic structures could match, but like maybe, yeah, first as an algebraic variety or, yeah, holomorphic symplectic.
So just
Yeah. Yeah.
first question. So C was the class.
C, yeah, it's the collection of the conjugacy class of all formal monodromies. So basically,
Oh,
yeah, the convex, so if with respect to this, for example, it's the conjugacy classes of all blocks associated to all QIs in this lambda for every singularity. And such a QI, it's, yeah, it's in one-to-one correspondence with a leaf on a fission tree. So
is how to read from the tree these NIs.
so yeah, no, you have to, so that's why there is a pair with the tree and the conjugacy class. The NIs are the dimensions of the, so it's a decorated tree. You can view the pair like the tree with the conjugacy class. So if from the tree, like stricto sensu, there is no NIs, but I mean, I can decorate the tree with the NIs or the conjugacy classes. Yeah. Yeah, but the kind of, yeah, the tree itself, like, yeah, forgets the NIs, but so then I can.
And another question. So at the end of the day, now you introduced the name.
Yeah.
The name.
Fission tree. Yeah.
This then.
So no, yeah, that's true. Yeah, to save time, yeah, I didn't explain what I mean really by wild non-abelian Hodge spaces. It's like just because like there is this like non-abelian Hodge correspondence where like you can view objects on the three sides, Dolbeau side, like Durham side, and Beatty side, and there are like those isomorphisms between them. And so yeah, you expect that. I mean, like the general philosophy is that you would accept that like really this whole structure is like common in the different, coming from the different fission forests. I mean, like ideally, in some cases, I think it is known. I mean, like all the structures on all the sides basically would kind of match. And so, yeah, so that's kind of the philosophy. It's not just like, because when I say wild character variety, I'm kind of thinking more like the Beatty context. But when I'm saying wild non-abelian Hodge space, it's like that I have more in mind like the three sides at the same time. And like the general philosophy is that, yeah, we expect that like the isomorphisms should extend somehow, yeah, on the general picture. But there are only, yeah, I think very few cases where this is like everything is like rigorously done. But that's the general expectation. This the forest, it's more kind of, it's more on the Durham side, I would say, because I mean they come from the I mean, yeah, the motivation for defining them comes from the Durham side because it comes from the Touritten level decomposition of the. But then, I mean, once you get them, you can define them and like define the wild character variety, kind of forgetting from where it came from, if you want. So you can define the, yeah. So, any further questions?
You see, I suspect it is implicit in your. When you have, so can you go in the pic where you have a picture of the division? No, division.
Yeah.
So here, for each point of the base space, you can introduce. I mean, you have. Well, here you have several singularities. At the regular ones, you can introduce the formal normal.
Yeah, exactly.
I suspect that you take for granted that when you deform, I mean, dependence of the formal normal.
Yeah.
On the base.
Yeah. So yeah, no, so yeah, I'm not claiming that like everything in this picture is rigorously defined. So namely, like Philip Boalch has done is like he kind of defined like those wild character varieties like on the Betty side with like their quasi-Hamiltonian structure, etc. And like in his ANL paper, he basically shows that there is like this you can assemble them in this like locally constant vibration on the Betty side, and then like this translation, yeah, on the Durham side, I expect, as I think you mean, that like to make it fully rigorous, yeah, you would have like some work to do in general, like to show that like I mean like this behaves well in like families, like with respect to the parameters. So right now it's more like a heuristic like pictures, but like this passage, I don't think that it has been like rigorously done for like any irregular types. I think Philip says something in this case, like in some old papers in the case with like basically Dubrovin connections. I think he.
Well, I can tell that exactly the same condition, genericity condition that you had in some slides.
Yeah. Yeah.
As if I'm not wrong, essentially that genericity condition has been proven, for example, by Hodge.
Yeah. I remember we talked about that. Yeah.
Formal.
Yeah. So yeah, here the motivation is more like from the Betty side, kind of this condition is natural from the Betty side, otherwise the shape of the Stokes matrix is changed. And like, yeah, if you impose this condition, then you can build like this Betty side vibration. And this seems consistent with what you are saying, that Schäfke proved that like given the same condition, you can build the Durham side vibration. But then, yeah, I mean, like, look, I guess the pieces of the puzzle have still to be assembled if you want to, yeah, to claim that everything in this picture all is like fully rigorous. But so I'm really not claiming that.
But for non-resonant irregular singularity, very simple, nice. For the resonant,
Yeah, maybe.
Work by sharp from the one.
Mm-hmm. Yeah.
Beyond the best work, which the best expression was that paper by Sharp.
Okay. Maybe I can go on. So yeah, no, so I explain kind of how to kind of reduce the data that I need to define a wild character variety to this more like combinatorial data, this like fission forest. Now I want to speak about how can you find or maybe guess or conjecture that there are some isomorphisms between wild character varieties defined by different fission forests. Yeah, maybe first let's mention some history. So so this question of relating different isomonodromy systems or different moduli space of connection already has some history, and maybe the simplest setup where such correspondences appear is like the so-called Harnad duality, which relates connections of this form. So on the one side you have a connection like this, and then on the other side you have a connection like this. So here like A, P, Y, and Q are linear operators, so like matrices between two vector spaces V and W, and like the source and the target of like the map is indicated by this diagram. And you see from this picture, Harnad duality, you just kind of swap the role of V and W, and you get those like dual kind of connections. And so in this case, what are the irregular types? So they are on both sides connection with one irregular singularity at infinity with a pole of order 2 and regular singularities at finite distance. And the thing is that this recipe, this duality, it really corresponds to an isomorphism between the corresponding moduli spaces on both sides, and not just between that, but like the isomonodromic deformation equations on both sides are actually equivalent. So maybe that's the simplest instance of such correspondences between moduli spaces of connections. Maybe the next simplest case is the so-called simplized case, which was extensively studied by Boalch in several works. Now this corresponds to a singularity structure, which is the following. So you have an irregular singularity at infinity of order at most 3. This is a typo. And you also have regular singularities at finite distance. And the idea is that, yeah, any such connection, the formal data of any such connection determines, yeah, what we call the supernova quiver, plus some extra data, which goes like that. So you have a core whose vertices basically corresponds to the different exponential factors at infinity of the connection. And it is a complete k-partite graph. So you have k subsets of the core, and each vertex of one of the subsets is related by an edge to each vertex of another subset. So here's an example like this. I have k equals 3 subsets, like with the 3 colors, and each vertex of one subset is related to a vertex on another subset. So that's the core of the diagram. And then to this core, you will glue legs. And those legs, there is a way to encode with like such a linear quiver, a conjugacy class in GLN. So they encode the conjugacy classes of the formal monodromy. So to every simply laced connection, you can associate something like that. The black points, they are the vertices of the legs. So yeah, maybe. So yeah, the idea is, yeah, it's a result that, yeah, basically a conjugacy class in GLN can be encoded basically by a quiver variety like that, and the dimensions of the vector spaces are related, like it can be defined from the characteristic polynomial of any matrix in the conjugacy class. Yeah, and the statement is that, so given like this data, this supernova quiver, actually you can reconstruct the moduli space of the connection, but you can reconstruct not just one moduli space, but actually you can reconstruct k plus 1 moduli spaces, which are all isomorphic. And basically, yeah, the way to do that is that like you can single out any of the k subsets, and this gives you, yeah, k different readings of the diagram. Or you can like single out none of those k subsets, and it gives you the one extra reading. So here in this example, I have like 3 subsets: this one, and this one. And then schematically, like there is one reading which corresponds to, yeah, not singling out any of the sets, one reading which singles out this subset, one reading which singles out this one, and one reading which singles out this one. And yeah, each of those readings defines you, yeah, a moduli space of connection. With, in general, they will have different ranks, different number of regular singularities, but they are all isomorphic. And actually, in this case, we have better, is that there is this open dense part of the moduli space corresponding to restricting on connections on the trivial bundle over P1, which is exactly isomorphic to a Nakajima quiver variety, which is defined by the quiver plus like some extra data that I didn't mention. And so not just the moduli spaces are identical, but the isomonodromy systems, like the equations describing isomonodromic deformations for each of the reading, are equivalent. So in this case, yeah, we have this nice larger symmetries between, yeah, k plus 1 moduli spaces in this simplest case. And yeah, the goal of what I want to explain is that we can actually partially extend that to connections with absolutely arbitrary singularity data on Pi1. Yeah. Yeah. No, go ahead, whatever. Yeah. Yeah. This is an yeah. The one nice thing is that most kind of known instances where you have different Lax pairs for Painlevé equation fit into this framework. Yeah, for example, for P2. So, but for P2, it's not for P2. You kind of need what I am going to tell in a while, because one of the Lax pair, like this Flash-Canuel one, if I'm not mistaken, there is like a Poincare rank 1/2. So it's so there is some ramification. So it doesn't belong to the simplified setup. So no. So some of the I will show maybe in like a couple of yeah, in a minute, like the diagrams for the Painlevé equations. And so the ones for Painlevé 6, 5, and 4, and maybe that's all, they fall into this simply laced framework. But the other ones, they don't. And so you need, yeah, what I'm going to explain next if you want to do the same. Yeah.
Why?
So it's some kind of generalization of finite duality. Maybe if I explain this slide, it will become slightly clearer. But it's some kind of it's an extension of finite duality. So yeah, so you have this kind of nice like k+1 LET in the simply laced case, but like you can view it in a slightly more abstract way. There is an underlying like SL2C symmetry basically behind that, and yeah, what is the idea? So you can consider this veil algebra, which is the algebra of differential operators over the affine line. So C, which I view as like pi1, where I remove infinity. And so the thing is that any matrix A in SL2C defines for you an automorphism of this veil algebra by this prescription. Z becomes AZ plus B partial Z, and partial Z becomes CZ plus D partial Z. And so like this, such an automorphism, it can induce a transformation at the level if you consider like an ordinary differential equation. Like you have a polynomial into those variables Z and partial Z, and you get a new polynomial. You can consider the corresponding equation. And such an equation, it's quite close to a connection. And with a couple of caveats, basically this thing, it induces, like for any matrix A in SL2, a transformation of irreducible connection on open subsets of Zariski open subsets of pi1. And yeah, a remarkable fact is that for a connection being of simply laced type, it's preserved by this SL2C action. And yeah, the more kind of abstract way to understand like this simply laced case is that like those readings of the supernova diagrams, they exactly correspond to the different kind of configurations of singularities that appear in a given SL2 orbit. And yeah, to echo your question about Hanat duality, basically what happens is that Hanat duality, it corresponds to the Fourier transform, and the Fourier transform is just a particular matrix in SL2 where you have Z becomes partial Z and partial Z becomes minus Z. So yeah, the Hanat duality basically corresponds to this particular case, but there is this larger symmetry, and it induces like those k+1 readings of the diagram that Boalch had. Okay, and so yeah, now what I want like in the rest of my talk, yeah, I want to extend the story to arbitrary formal data, but yeah, you have a question? No, okay, so 5 minutes. Okay, well, I have to be a bit quick. Okay, so a first step that is something that I did in my PhD is kind of I defined what is the natural extension of like the diagram if I go outside the simply laced case. So now I have arbitrary formal data of pi1. So it's the same idea. Like I have a core, which is determined, whose vertices are basically the exponential factors of the connection, and legs, which correspond to the formal monodromies. But now, yeah, it's a bit more complicated. I can have like loops, and I can also have like edges with like, or loops with negative multiplicity. So it's not really a quiver anymore, and there is no quiver variety, but like the moduli space still has the same dimension, the dimension given by the same formula that is the formula for the dimension of a quiver variety. And the interesting thing that I showed in my PhD is that this diagram is invariant under SL2C. And like, yeah, and I can draw here the examples of the diagrams for the Painlevé moduli spaces. So those ones you see, they fit into the simply laced framework, as you were mentioning. For Painlevé-2, actually one of the, it doesn't fit into the simply laced framework, but it's like this, but it has no loops and negative edges. And for Painlevé-3 and Painlevé-1, also really need this generalized framework. So you see, for example, for Painlevé-3, if you have a diagram with like a negative loop like this.
What it means to have a negative loop?
I mean, it's just, I define like an adjacency matrix. Basically, I have like a set of, by diagram, I mean, I have like vertices and I have a number of edges, which is defined by an adjacency matrix, which is symmetric. And I just allow my entries in the adjacency matrix to have, to be negative possibly. And I call that a diagram. So if I have a quiver, all entries will be positive, but I say, okay, let's allow having negative entries. and I call that a diagram. That's why I'm not calling that a quiver, because it would be too big abuse of language. Okay, now I only have 5 minutes. Okay. So the idea is that if I act by SL2 for a matrix in an open dense subset of SL2, starting from any connection, I will have a connection which is what I call of generic forms. It means it will be a connection at infinity, and all its exponential factors at infinity will have a slope less than 2. So they will be of the form something times z squared plus something with exponents strictly less than 2. And this is what I called generic form. And the thing is that the problem with the diagram is that it's nice, it's invariant under SL2, but it's not enough to do the reading of the diagram. In the simplest case, I could start from the diagram and directly look at it and get all the k+1 readings. But in the general case, the diagram is not enough. I will need some extra data. And this is where I will need the fission trees that I was mentioning before. Basically, all the data that I need is the fission tree of any connection of generic form in this SL2 orbit. So in particular, in the generic form, you just have one singularity at infinity, so the fission forest is just one fission tree. And so the main statement is that if I start from like a fission tree of generic form, so all vertices have height less than 2, and I also have to take some conjugacy classes. From this, I can explicitly know these data are enough to construct other fission forests with conjugacy classes explicitly just from this combinatorial data. And those data are none other but the classes of admissible deformations that appear in the SL2 orbit of any connection of generic form having this initial formal data. So it can, as in the simply laced case, there is a finite number of admissible class of admissible deformations of such formal data in an SL2 orbit, and I can explicitly describe them. And if one expects, it's not fully rigorously proven in general that these SL2 transformations induce isomorphisms at the level of character variety, but it should be true. So if you believe that, then those formal data gives you k+1 classes of what I call representations of the same wild character variety of the same moduli space. And so what do they look like? Those representations, I have the generic one, so the initial one, and then for each, there is a canonically defined integer k, which is basically the number of principal subtrees in my generic tree, which is also the number of vertices of height 2. And this defines canonically my integer k. And for each k, or basically for each subtree, each principal subtree, I have a non-generic class of representations. And maybe let me show you this on an example, which corresponds to the Painlevé-3 moduli space. So here the generic tree is the following. So you see I have two principal subtrees corresponding to the two vertices of height 2, represented in two colors. And from this, I can also, so this is the generic reading, I can reconstruct from this the other fission forests. And I can reconstruct a lot of information, for example, the rank, the number of singularities. And what I skipped is just, I'm saying that, I can have an explicit, description, an explicit statement for this rank, number of singularities, and some information. You can really get the fission forest of all the representations starting from the generic one. And maybe just to conclude, if I still have 1 minute, the intuition behind this is that when I have a coefficient q of generic form, I can look at this coefficient a. It's a over 2 z squared here. And I call this the Fourier sphere coefficient because SL2C acts in a very nice way on those coefficients, actually. It just rotates them according to the corresponding homography. And the generic case, it just corresponds to the case when none of those coefficients is at infinity. And the generic reading, the ice generic reading, it corresponds to the case where one of those coefficients is at infinity. So which explains why there are k+1 situations. Either you have none of those coefficients which is at infinity, either you have one of them. And so you have k+1 cases. And just to conclude, yeah, I can show some examples related like to some different Painlevé-like pairs. So for example, for Painlevé-1, the generic tree would be that. And I would have like those two different readings with the ranks and number of singularities. And for Painlevé-2, we'll have that. And I will have like, this is the generic tree. I will have 3 different readings. And yeah, if I'm not mistaken, so this one is the kind of standard Jimbo-Wimi-Wa one. This one is the Flash Canuel, for example. And I have like, the generic one has always a higher rank. Okay, so yeah, that's basically everything that I wanted to say. So we have this kind of nice combinatorial description of wild Riemann surfaces that conjecturally correspond to isomorphic wild character varieties. And there are still a few questions like, yeah, can we really prove that there are isomorphisms? Our work with Andreas covers like some cases. For example, it covers the case of Painlevé-1 between the 2 readings. And then, yeah, there is this like Deligne-Simpson question, is like the moduli space non-empty? And then there is also the further question, could we relate not just like the moduli space, but also like the families of moduli space, so the isomorphic deformation? And yeah, I guess morally it should be more or less true, but I mean, there would be some work to do that like properly and like, yeah, understand like, the details. So yeah, that's all I wanted to say. Thanks a lot. Yeah, sorry. Yeah.
Page with many diagrams.
The Painlevé ones?
Later.
That one?
Yeah.
Yeah.
You see the apples, but I don't see how you come from one to the other diagram.
Ah, yeah. But I mean, you can see there is like a family resemblance. Like you see this, it kind of becomes this, but there is some change. So it's, and like, and then this, like, yeah, here, like the 2, yeah, they kind of disappear. You just have regular singularities. So I mean, there is a recipe. Yeah, yeah. So basically, yeah, you have to, roughly speaking, you have to multiply like those heights, which are like the exponents appearing like in the exponential factors by some rational number, which depends on on the slope of on the slope of some coefficient appearing in Q. So you have to but you can write down explicit. I mean, you can kind of forget. Yeah, you can write down explicitly just from the generic fission tree at least. But yeah. Ah, yeah, I'm vaguely familiar. I'm not sure. I don't know much about this, but I'm not sure that this kind of like diagrams would behave well with respect to those folding transformation. I guess not really. Also, with respect, for example, like to these questions of coalescence, it seems like they don't behave really well. What they behave well with respect to is like this SL2 transformation. Which and so these changes of those different lax pairs, but yeah, it won't behave well with respect to all possible things that you can consider on connections. But yeah, still I find it's a nice toolbox to have.
So let's think. Okay.